Introduction to projectiles. Okay? A projectile, by definition, is any object traveling through the air in unpowered flight. Okay? The unpowered part is the most important part. Okay? A plane is not a projectile. Okay? It is using energy to propel itself forward. Okay? Therefore, it is an aircraft. Right? A projectile would be like a baseball that you throw to your friend while you're playing catch. Okay? A bullet, an arrow, okay? Something like that. That's an unpowered flight. It's not using any, there's no forces other than gravity that are contributing to its motion. Okay? That is a projectile. The simplest projectile is just throwing something straight up in the air. Okay? So if I throw it straight up in the air, it comes back down to me. Okay? Once it leaves my hand, what's the only force acting on it? Gravity. Okay? And so as a result, it goes up, okay, but it's accelerating down, so it slows, it slows, it slows. It reaches its maximum height, where for an instant it does what? It stops, right? For an instant it stops. And then it falls back down, and then it falls back down again at 9.81 meters per second squared. It's just now moving downward. A projectile is always accelerating downward. It may not always be moving downward, but it is always accelerating downward because gravity is what causes projectile motion. Okay? Now, in your experience, okay, projectiles, when you throw something, or maybe if you've got like the hose in the backyard, okay, projectiles always seem to follow what shape? I heard somebody whisper. An arc. An arc. Yeah, projectiles always follow an arc. I mean, if you've ever played catch, okay, watched a football game, watched a baseball game, okay, the ball always travels in an arc. Play golf, okay, any of that, it always travels in an arc, okay? And that is because those type of projectiles, at least, initially start with some upward velocity, okay? And gravity has to haul them back down. Now, the nature of projectiles that we want to focus on is that they're actually moving in 2 dimensions at the same time. Okay? A projectile is moving vertically and horizontally. Kind of like the boat questions that we did back in the vector part. Okay? A boat was moving both across and downstream at the same time. Right? Well, for a projectile, it is moving vertically and horizontally at the same time. Okay? If I want a projectile, let's say it's, I'm a quarterback and I'm throwing a Hail Mary pass to the receiver, okay? If I want to make sure that ball gets there, okay, and it's a really long pass, what do I do differently than a really short pass? Probably be 2 things I would change about the way I throw that ball.
The arc and the speed?
Yeah, the arc and the speed. Right? If I want to throw a Hail Mary pass that's going to be 40 yards, right, I'm not only going to have to throw that thing as hard as I can, but I'm also going to throw it at a bigger angle. Okay? Think about this, and if you ever did this as a kid, played with a hose, right? Your little brother, you're trying to get him with the hose, but they're a little too far away. All you had to do was angle the hose slightly upwards, and the water would travel further. Okay? The water wasn't coming out of the hose any faster, okay, but it went further. All you did was angle it. You gave it more time in the air. And so it naturally traveled further because it had more time to fly through the air. So if I want to make a Hail Mary pass, I've got to throw it harder and higher, okay, or at a higher angle so that it has more flight time and thus can travel further. Okay? If I'm just, making a short toss, okay, that's nothing. I don't use much of an angle, okay, and I don't have to throw it very hard because I know it's not going to be in the air for very long. Okay? Making some sense? Sometimes it really helps to just think about the times where you've actually done that in your life and go, oh yeah, okay, that totally makes sense. Okay. So we're going to be looking at today the simpler types of projectiles, okay, like if you ran off of a diving platform. Okay? If you run off of a diving platform and you don't jump, you just run straight off, okay? Do you just fall straight down or do you travel forwards? What do you think? I travel forwards or do I fall straight down if I run off of it? Travel forwards, yeah, absolutely. Okay, we're gonna do something like this, okay? You'll have, here's your diving platform. If you run straight off of there, you're gonna do this. Okay? At first, you'll be moving, it'll seem like you're moving more horizontally than you are vertically, okay? And for the first few instances, that's true, okay? But as you watch that person, does their motion end up starting to look like it's almost entirely vertical? If you watch a car drive off a cliff in a movie, because that's like this trope that always happens, is cars drive off cliffs and then they blow up, they don't. Okay? But it looks like at the end they're just going straight down. They're not. They're still traveling forwards, but they've just gotten going so fast vertically that it looks like all they're doing is move vertically. And the reason for that is horizontally, they don't accelerate. Okay? Any projectile, its horizontal part is constant velocity. Once I throw something, that's as fast as it can go horizontally. But gravity's going to grab it. And gravity's going to accelerate it, but it'll only accelerate it vertically. So strangely enough, the reason we get this type of a shape, okay, for something that goes off of a cliff, okay, is because it's actually moving at a constant velocity horizontally, but going faster and faster vertically. So at the beginning, it's not moving very fast vertically yet, so most of its motion is horizontal. Okay? But it doesn't take very long at 9.81 meters per second squared for the vertical part to be pretty dominant, okay, and to look like, it's just falling now. Okay, does everyone kind of follow me there? So what we're going to look at a bit in this part of the unit is, well, bad movie physics. Okay? Projectile motion is like the place where you can always tell whether they took the time to plan something out, like a stunt, or whether they just sent it to the CG guy. Okay, because that's what they do nowadays. Instead of like making it for real, which is expensive and dangerous, okay, they just send it to the CG guy and he sits in the dark and makes it happen. Okay, well, you can almost always tell, okay, at least in older CG, whether it was done by CG or done for real. And I don't mean because it looks like, like it was obviously computer generated. Just the physics of it isn't right. And you can just see it. You can look at it and go, stuff doesn't move like that, and you can just observe it. Okay? And so that's an important thing that they've used in modern movie making, okay, in their building of algorithms for CG. Okay? They've built algorithms so that when they punch in, we want this car to drive off of a cliff, the algorithm knows, okay, it needs to do this and this, it needs to move horizontally constantly, it needs to accelerate downwards at 9.81, okay, and it can model that and make it look far more realistic than back in the day when they basically had to animate every little bit of it on the way down. Okay? That always led to bits and pieces that looked wrong, visually wrong. Okay? Everyone kind of follow me there? So it's become quite a bit better. You almost don't notice it anymore. But I'm going to show you some early CG stuff that makes it looks awful. Okay? And you can tell right away that it looks fake. All right, so the big thing with projectiles here, guys, okay, as we said, it's unpowered flight. There's two dimensions, horizontal and vertical. Okay, the vertical dimension undergoes accelerated motion. So we're going to be using all those formulas that we've been going over. Okay, there's going to be an opportunity for basically every acceleration formula we've covered to be part of projectile motion. And then the horizontal part is constant speed or uniform motion. So V equals D over T will govern that part. Okay, so this is where Newton comes in. Okay? Projectiles do what they do because of gravity. What goes up must come down. Okay? Even if it doesn't start up, okay? It's got to come back to Earth because gravity is going to pull it that way. Okay? So gravity pulls the object towards the Earth while it travels horizontally. That means that an object fired horizontally will have the same flight time as an object that's dropped. Here's what that means. I take two identical bullets. I put one in a rifle, and I have the other one sitting right beside it, not in a rifle. if I pull the trigger on the rifle and drop the bullet, they will hit the ground at the same time. How many people think, no way, Coderre? That is not true. There's no way that a bullet fired from a gun can hit the ground at the same time as a bullet dropped from exactly the same height. It seems counterintuitive, but it's 100% true. I never said they'd hit the ground in the same place. Okay? I said they'd hit the ground at the same time, because they're both going to be affected by gravity. Gravity is going to drop them the same distance. It will take them both the same amount of time to fall that distance. One's just traveling horizontally while it doesn't. But they will, in fact, hit the ground at the same time, but obviously not in the same place. Okay? Now, that is, of course, assuming that I did have the gun oriented horizontally. If the gun was oriented at an angle, then that wouldn't be true. Okay? But if it was angled horizontally, or not angled, just pointed horizontally, they will hit the ground at exactly the same time. Okay? Now, I believe I have, I'm going to show you here this ad, and it was from like the late 90s, but it was for this new Lexus sport sedan. Okay? And someone came up with this great idea, and they said, we're going to market this sports sedan as being very fast, which at the time it was. It was a very powerful car for the time. We're going to tell people that it's faster than gravity, because people naturally understand how fast gravity is. People have a fear of falling because they know gravity accelerates you. So if we can tell them that our car is faster than gravity, they'll want to buy it because they'll be very impressed. And they were right. Okay? This advertising campaign worked incredibly well for Lexus, okay, in selling this Lexus IS 350. Okay? So here's what they did. They had two identical Lexus IS 350s. One was suspended from a helicopter. The other was on an airport runway. Okay? They held the Lexus that was on the helicopter above an X, basically on the runway. And they raced them. Okay? By dropping the one from the helicopter. And they would race it with the car on the ground. The car on the ground can get to that spot first. It's faster than gravity. Okay? Now, with that initial setup, does that sound like that's a fast car? I mean, gravity's fast. No car accelerates at 9.81 meters per second squared, unless it's being dropped from a helicopter. Okay? That is a ridiculous rate of acceleration. If that's all you pay attention to, which is of course what the ad wants, then you fall into the trap. And you go, this car is really fast. It's faster than gravity. I gotta go buy one right now. Okay? And people did. If you watch the ad carefully, you'll see where they take advantage of it. Okay? So I'm going to play the ad, and I want you to see if you can find out where they're not telling the whole truth. Okay? In that question, how are they tricking you?
The car had already gotten up to speed by the time they dropped it.
Exactly. They didn't both start from rest. They both started from rest. The car on the ground had no chance. None at all. They dropped the drop car when the Lexus IS 350 on the ground was traveling at its maximum speed, which was still an impressive number, okay? But that means it gets to travel at its maximum speed for all 4,000 feet. Does the car that's dropped get to do that? It starts from rest. Now granted, it's going to accelerate at 9.81 meters per second squared, that's fast, but it'll never go as fast as the car on the ground. Why? If you drop something, does it accelerate all the way to the ground in the real world? Or does it stop accelerating at some point? At its terminal velocity. Okay? All objects on Earth have a terminal velocity. It's based on their wind resistance, basically their shape. Okay? They rigged this whole thing so that the car on the ground could win. When they dropped that car from the helicopter, they put weight in the back so that it would fall flat. That is the least aerodynamic direction for it to fall. The bottom of a car is full of all sorts of edges, and it's flat, and it was horrible. Okay? It had no chance. Its terminal velocity was probably only about 130 kilometers an hour. Okay? That would have been the fastest it could have possibly gone. The car on the ground had every advantage. Okay, yes, did the car that fell accelerate? Yes, it did. Okay, is the car on the ground fast? Yes, it did, but not as fast as they led you to believe. Okay, it's those little details that, if you have an understanding of physics, let you see through people trying to take advantage of you. Okay, and that's what advertising is all about. Give you this impression, leave you with that impression that you won't think about, but you'll just go with. Okay, that's what they want. But if you understand physics, you see where that one breaks down. Okay, the Mythbusters actually did a whole episode on that ad where they dropped a car from a helicopter and raced it with a car on the ground. Okay, car on the helicopter won every time. Well, they only did it once, but okay, it was every time technically. Okay, but their big trick, the big problem they had was getting the car to fall the way it did in the ad. Most cars have their engine where? Up front, right? You drop it from a helicopter, what does it do? Points down like this. If it points down like that, it's now falling in its most aerodynamic dimension. Its terminal velocity is a lot higher. It's falling nose first. Okay? So they had to rig it. That's how they figured out that they had to have rigged that car to fall flat. Okay? They actually dropped like 3 or 4 cars from a crane, okay, in a shipping yard until they got it to fall at least half level. Okay, so is this making some sense? Okay. So in any situation where we've got a projectile flying through the air, gravity is going to pull it back to Earth. Okay? If we're talking about hitting a target in archery or in rifle sports or anything like that, okay, can you aim at the bullseye and hope to hit it? You absolutely can't. Okay? If you aim at the bullseye, you will always hit where? Below or above? Below. Gravity is going to pull that arrow or bullet or whatever it is that you're shooting down. Okay? So if you aim for the bullseye, you're going to hit below. If you even throw darts, okay, if anyone even just like throws darts at home, you can't aim for the bullseye. You got to aim above it. You got to correct for drop. Okay? That's the big challenge with it. Okay? Playing darts in zero gravity would be like super easy. Actually, no, it wouldn't, because when you throw it, you'd move backwards. That'd probably make it hard. But you wouldn't have to worry about drop. It would fly nice and straight, okay, in zero gravity. Okay? In gravity, you've got to correct for that drop. So if you're a marksman, okay, if you've got a scope of some kind, the scope can be adjusted to make those longer shots. Okay? How many people have seen the movie Saving Private Ryan? Okay? So in Saving Private Ryan, there's a scene where Vin Diesel gets shot, spoiler alert. Okay? And in that scene, their sniper is kind of having a showdown with the German sniper. And they figure out where the German sniper is. They figure out that he's in this bell tower a ways away, and their sniper adjusts his scope. He says he's about 800 yards, that's 2 clicks. And he clicks his scope twice. Okay? When he clicks the scope, what he's doing is pointing the scope downwards to correct for the amount the bullet will drop in flight. So now, in order to get his target in the sights, he has to lift the barrel above the target. So the barrel isn't pointed at his target, it's pointed above it. The scope is pointed at his target. Okay? Then, when he pulls the trigger, the bullet will go up and come back down and end up on target because he corrects for how much gravity will allow that bullet to descend during its flight. Okay? Okay? That sort of makes sense? It's the same thing that we unconsciously have to do. Okay? And if you've ever like done the dunk tank, where you're trying to dunk somebody and trying to hit that little thing with the ball, you got to aim a little bit above it to correct for the drop or you're going to miss. Okay? That's how it works. Okay. We're going to watch this video, then we'll do this question. Okay? Okay, so let's have you copy this one down. Here are the things we're going to assume about the situation we just saw with Rebel Without a Cup. Okay, with James Dean versus the greaser. Okay? We're going to assume that the cars drove off the cliff at 25 meters per second. There was no ramp, they just drove horizontally, straight off the cliff. Okay? And we're also going to say that the cliff was 60 meters high. Okay, so that means the car has to fall 60 meters down before it hits the rocks. Here's what we want to find. I want to be able to calculate how far from the base of the cliff the cars crash. Because maybe I'm search and rescue and I need to go find this guy. Okay, so I need to know where to look. It's dark. Okay, I can't see. So the cars are doing two things. They're traveling horizontally, and we know they're traveling horizontally at 25 meters per second. And they're accelerating. So there's two pieces of information that are missing here. Okay, what are the two pieces of information? They're both vertical. What's our acceleration vertically? 9.81. Okay, that's one of the pieces of information that's missing. Okay, we know vertically speaking, they're going to travel 60 meters down. They're going to do that at 9.81 meters per second squared. And we know one other thing vertically. These cars drove horizontally off the cliff. What was their initial vertical velocity? Okay. Zero. Okay? If they drove horizontally off the cliff, they were not moving vertically at time zero. That's the big thing you need to know for any horizontally projected projectile. If it is projected straight level, its initial vertical velocity must be zero. It isn't moving up or down if it goes horizontally at time zero. Okay, so that's the other piece of vertical information that we have. All right, whenever you're doing a projectile question, the best thing to do is break it up into its horizontal and vertical parts, okay? Because they're gonna have different givens. The only thing that the vertical part and the horizontal part have in common is time. Okay? You are traveling both horizontally and vertically for the same amount of time. Because once the car crashes into the rocks, it's not doing either one anymore. Okay, is that fair? Okay. So here's what we know. Vertically speaking, the object undergoes accelerated motion. Horizontally speaking, it travels at a constant velocity. This question told me that constant velocity. It said the cars drove off the cliff at 25 meters per second. So I know the horizontal velocity. It is 25 meters per second. What this question wants is my horizontal displacement. This blue line here is how far the object travels, the car in this case, how far it travels horizontally. So I am looking for D. There's actually two D's in this question. There's the vertical displacement, okay, that's 60 meters, and there's the horizontal one that we don't know yet. What do I need in order to calculate the horizontal displacement? Time. Okay? I don't have the time. Could I calculate the time with my vertical information? Okay? I'm pretty sure I've got a formula that's got D, acceleration, and initial velocity, and time in it. Pretty sure. Okay? And I think it's this one. You know, that formula I said you'd never have to use to solve for time? Unless initial velocity was 0. Is initial velocity 0 here? Okay. So I should be able to solve for time. Okay, so I'm going to divide both sides by half of a and then square root. So it'll be d over 1/2 of a all square root. Okay, so for this question, that'll be 60 meters down divided by 1/2 times 9.81 meters per second squared down. Okay. I can make them both negative if I want, but there's no point. Okay, I'm shortcutting. Half of 9.81 is 4.905. I'm just shortcutting that number there. Okay, so they're falling for 3.5 seconds. That's a long time to contemplate your doom. In fact, that's more than one scream. You probably have to like take a breath and scream again, okay, for 3.5 seconds. Okay. So 3.497 seconds is my time. That's the same amount of time that they're traveling in the horizontal dimension. So I can bring that number over. It's the only number that is shared by the vertical and horizontal parts of a projectile question. Okay, can I calculate how far that thing travels horizontally now? Okay, I've got V and T. Okay, they travel further horizontally than they do vertically. It doesn't look that way in the movie, but that's because I made up the numbers. Okay? But you absolutely could if you go off that cliff fast enough. Okay? You could absolutely travel further horizontally than you do vertically. Okay? So 2 significant digits there, 87 meters from the base of the cliff is where I need to look for the wreckage. Okay. Now, when it's all said and done, all you really had to do there was one acceleration problem and one v equals d over t problem. Okay? Projectile motion always breaks down to that. Okay? When we start dealing with angled projectiles, you'll have a little bit of trigonometry as well. Okay? But what they basically come down to is one part of them is an acceleration question, one part of them is a v equals d over t question. Okay? Because you're dealing with vertical and horizontal parts of the motion. Everybody okay with that idea? All right. So for this type of question, there's only a few ways I can write a question like this. I could do it this way, give you the height of the cliff and the speed they go off at, and ask you to calculate the horizontal distance traveled. Or I can give you the horizontal distance traveled, the height of the cliff, and ask you how fast they drove off. Or I can give you the speed they drove off, the horizontal distance, and ask you for the height of the cliff. That's it. There's only 3 ways I can ask that question. Okay? And they all involve the same formulas. It's just what order do you do them in. Okay? In the end, the thing you're going to have to find for any projectile motion question is time. If you have the time, then you have something that can be used on both parts of the question. It's the most important piece of information in a projectile question because you can use it horizontally and vertically. So more often than not, you have to find it using this one so you have it for that one, or vice versa. Okay, time is the thing you will always have to. Okay, questions on how that worked? Okay. I mean, when it comes right down to it, all we did was algebra, right? Like we manipulated an acceleration formula, we manipulated v equals d over t. Okay, there's really not a lot to it, it's just asking you to incorporate it into something a little different. Okay, we got to do de Paul. Okay. Let's see if we can figure this out. All right. Bomber is moving at 200 meters per second. Okay? And the bomb travels horizontally 1,800 meters from its point of release to impact. So while Major Kong is yee-hawing all the way to the ground. Okay? So we know it's traveling horizontally at 200 meters per second. We know it's going to travel horizontally 1,800 meters. What altitude did they drop the bomb from? Okay, I want to know what altitude that would be the vertical displacement of the bomb. Okay, what altitude did they drop the bomb from if we know these two pieces of information plus two others that I haven't outright stated that are true? Okay, give you a minute or two on that one. Okay, remember to break this up into your horizontal and vertical pieces of information. Okay, you definitely want to separate those two things. Okay, we are given two very obvious horizontal bits of information. Okay, the stuff that's less obvious is the vertical stuff. Okay, they are flying straight and level when they drop the bomb. All right, what are the two pieces of vertical information that we have that are not explicitly stated? Applies to all falling things.
Acceleration.
We have the acceleration. Okay, guys, for any projectile, this number comes into play vertically. It's accelerating due to gravity. And because the plane was flying straight and level when the bomb was released, the bomb's initial vertical velocity was 0. No different than driving off of a cliff. It's exactly the same thing. So I'm trying to find the vertical displacement. I need at least one more thing. I either need VF, which I'm never going to get, okay, or time. Can I get time with my horizontal information? Then that's what I should do. Always try to find time. Time is the thing that you can use on both sides. Okay, so on this side here, time equals d over v. Okay, so 1,800 divided by 200 should be falling for 9 seconds, yeah? My mental math is right there. Okay, everybody all right with that? So I bring that time over here, and now I can solve for d. Just use that same formula we talked about before. Okay, since vi is 0, all I have to do is go 1/2 at squared, and I'll have the altitude of the bomber when it dropped the bomb. Okay, so we're just plugging in here 1/2 times 9.81. I don't have to make that negative because it doesn't change direction. It's only falling down. Okay, and then times 9 squared. Okay, so 0.5 times 9.81 times 9 squared. Okay, so it was 400 meters, right? Or 3.98 times 10 to the 2, or 398. We have 3 significant digits there. So 398 meters would have been its altitude before dropping it off. Okay? So we're going to spend lots of time. This whole week is going to be projectile motion, starting this. Wasn't it 397.8? 0.3. Okay, I didn't look closely enough. Yep, 397. Sorry. Okay, everybody all right with that? So here's the good news. While this is a new context for these things, There's no new skills here. This is still just doing acceleration problems and v equals d over t problems. You guys are good at that, okay? We just have to get the hang of, okay, how do I read and get the information I need from these kind of questions? So that's this week. That's what we're going to spend this week on. Okay? All right, good job today, guys.
You know,